So my name is Harm Knoops. I'm an atomic scale segment specialist for Oxford Instruments, and I also have a part-time assistant professorship at the Eindhoven University of Technology. I will talk about atomic layer etching, and then we'll focus on plasma aspects and process examples. So maybe briefly, background on Oxford Instruments. So I work for Oxford Instruments Plasma Technology, which is one of the business units. And you could broadly say that our mission is to do atomic precision on a production scale. We sell both to research and production. We make these plasma deposition tools, which you see examples of here. And roughly saying, these tools can be used to remove material, add material, so etch and deposit and grow. There we often talk about 2D materials and such. And why then atomic precision on a production scale? Well, in many devices in industry, device and feature size are decreasing. More control than ever before is required over features and layer dimensions. With these smaller dimensions, surfaces and interface quality is having an increasing impact on device performance. And techniques such as atomic layer deposition, which you see here, ALD, and atomic layer etching, ALE, could be really beneficial. And here you see kind of the merits of these techniques. So very good uniformity over a wafer area, so even over a large like 200 or 300 millimeter wafer. And for ALE, similarly, good uniformity over a wide area, so having the same etch removal over a big area. And even though it's then over a large area, you want actually then to have very good control, so removing on the nanometer scale every time the same amount, so growth control, etch control, having the same properties in 3D structures. For etching, having good selectivity, and then for etching, we can even distinguish between anisotropic, so only in the vertical direction, and isotropic. Basically mean, and again, I'm illustrating here both ALD and ALE for that helps, I think, the comparison. So they're both cyclical processes. So basically, the cyclical stepwise versions of the continuous processing, like plasma CVD and continuous etching or plasma etching, but here split up in two steps. So AB steps to stepwise grow or remove material. And how does it work? And from here on, I will focus just on ALE, on atomic layer etching. So it's split up in two steps, an A and B steps, and each step is separated by purge steps. And the first step, you would have a precursor or a reactant. This could be something like chlorine that reacts to the surface, bonds to the surface, and actually weakens typically the back bond to of the first layer. And that modified surface is then removed by a co-reactant. And the co-reactant could, for instance, be argon ions of a specific energy that then remove this layer. But those argon ions shouldn't have a too high energy that they would sputter the material below. And if you're in that regime, then you would be in self-limiting regime, and you would remove atomic layer by atomic layer. And you can see for each of the steps here below, you want to have sufficient exposure of the precursor to be in saturation. You want to have sufficient time between the steps to make sure you don't get mixing in the gas phase, sufficient argon exposure, for instance, to have full removal of that layer, and then sufficient wait step after that as well. So that's conceptually the process. And I think a very nice example of how it works is the prototypical ALE process, which is chlorine and argon, as I kind of hinted at already. And this is actually already reported in 1995. And we see here, it is actually chlorine gas. You can also use chlorine plasma, which is a bit quicker, but conceptually chlorine gas works as well. Reacting with the surface, reacting here with the silicon, making this silicon chloride layer, and that layer is then removed by argon ions of a specific energy. So the energy shouldn't be too high, and the flux should be sufficient to remove this layer. And by repeating these steps, you can remove layer by layer. So there's a certain etching feed, which is self-terminating because the chlorine doesn't, at the chosen temperature and such, doesn't continuously etch the chlorine, but just absorbs, and the argon just removes that top layer. And again here, conceptually, the process, and now also the comparison between anisotropic, so directional, and isotropic. So anisotropic means only etching in the vertical direction, and isotropic would be etching in all directions. So what you see here, basically, this could be ions. So then you remove this modified layer, but it's a directional process. And this a molecule, it can be a thermal process. So it could be even something like TMA, trimethyl aluminum, that reacts with this layer and removes that layer. And it could also be radicals. So it could be fluorine radicals or oxygen radicals that react. And radicals can collide multiple times and therefore can also be used for isotropic processes. So that's conceptually basically what is ALE. Now let's look at a little bit deeper at some plasma aspects, because that, I can imagine, for this audience is what people are maybe a bit more interested in. And then maybe it's good to say lots of stuff can happen. So this is from literature for continuous etching. And you can look at things like electron temperature, power, frequency, flow, pressure, stuff happening in the gas phase, plasma physics, plasma chemistry, things happening at the surfaces, plasma surface interaction, and also things like residence times of species. And you can imagine for ALE, because it's stepwise, it's even more complicated, because when you start a certain step, then the plasma is a certain way, and by injecting species or species coming from the surface, you will they're not a it's not steady state, so it can constantly change. That's an added complexity. Although actually that steps are separated, maybe also makes things simpler. One thing I would like to pick out is actually the effect of the ion energies in the typical in the ion step, and then one trend where ALE is also beneficial is actually to use relatively low ion energy. So in conventional etching, you typically use relatively high ion energies, and you can, as you see in these simulations from this nice presentation, you can amorphize the top layer, and for many devices, this is actually a non-desired effect. So you amorphizing this top layer doesn't lead to the best interfaces. You can have mixing also with things like chlorine, which is not great, and you have several nanometer thick layer. If you go to lower ion energies, this effect is much reduced and it's to a much thinner layer. And in ALE, you would typically need lower ion energies anyway, because you want it to be self-limiting and you don't want to sputter your bulk material. So how do we control these ion energies? Well, this is an example. This is actually our Flexol, our ALD system, but some ALE process can be done in this system as well. And conceptually, it's a plasma chamber similar to our etch tools. Just has a smaller ISP source. And we see here just an example of, okay, having the remote inductively coupled plasma source, looking at the plasma sheet, at the grounded substrate in this case, and it's a remote plasma, so relatively low sheet potential, relatively moderate ion energies. But then instead of grounding this table, we can also apply an RF bias. And by applying an RF bias, we can actually we create a negative bias voltage, which enhances the ion energy because the sheet voltage is higher. And we also see this in these measurements. These are oscilloscope measurements. So this is the grounded state. And these are two different sinusoidal RF voltages. So you see the time scales also. And you see the average voltage is negative. And this leads then to an increased ion energy. And because of this sinusoidal shape and ions traversing, maybe entering the sheet at different times, you also get a little bit of broadening of the shape. And I will come back to that as well. And this is for relatively high ion energies. And if you go to lower ion energies, you see that broadening is relatively mild, but you see here it does appear as well. So actually, if you do a very small bias, you can control the ion energy this way. And this is actually, I would say, the most standard and most typical way I would control ion energy. Maybe a difficult thing is these ion energies might require relatively low RF power. So that is something that we have specific hardware for this, but that can be tricky for some people. I do want to highlight, and this is some research done at Eindhoven University, where I'm, as mentioned, I'm partly involved, that we're also looking into tailored waveform biasing. And this is a collaboration also with ProDrive. This is not a standard, this is not a product yet, but I'll explain a little bit what it means here and what the aim is. So instead of applying an RF bias, we're applying here tailored waveform bias. And you see here this waveform, the shape, which is different than the sinusoidal shape. It's also different time scale. So this is more like 100 kilohertz instead of the megahertz. And what the goal here is to apply a certain voltage that gives a more constant ion energy, ion acceleration. But because you're also charging the surface, you actually have to induce a slope so that you compensate for that charging, and you have to periodically discharge the surface. So this explains this kind of maybe somewhat unusual slope where you apply a certain voltage, you apply a slope to compensate for the charging, and then you discharge. And this then leads actually, as you can see here in these measurements, and this is from the Farras paper from Eindhoven, to more narrow ion energy distributions compared to the RF biasing cases. And that could be nice actually if you're looking for specific ALE pros. So why is that nice? Well, if you actually look at atomic layer etching, then you typically have a certain ion energy window. So I mentioned if you go too high in ion energy, you can get sputtering. But actually, if you go too low, then you would maybe need lots of ions, or you're even below the threshold to remove for instance, this chlorinated surface. So then you have ink. I think conceptually that's quite easy. And in reality, that window can be quite small. So you see here, like in an ideal case, when the sputtering starts, but with the broadening, you might have a tail that already goes over this, is on that sputtering regime, and therefore you already start observing sputtering relatively early on. You could label that as quasi-ALE. I think there's a lot of discussion on the field. When is it ALE and when is it quasi-ALE, or when is it not ALE? I think for industry, the main thing is that it should be usable. So if a process has a benefit over continuous etching, then it's already of interest. But you can imagine these kind of cases, then it can be handy to have a more narrow ion energy distribution. And which typically at low energies you even have with RF biasing, I must admit. So that was some plasma aspects. I'm mostly focusing on the ions. And then I think to get a little bit more insight, it's maybe nice to look actually at some process examples of ALE. I only picked out a few because I think there's many examples, but I think this presentation would be way too long then. And I think I will focus on this hallmark ALE process, the one with chlorine and argon. And this is actually an RPP100 Cobra ALE system. And we see here it's an ICP inductively coupled plasma, quite large 300 millimeter plasma source meant for 200 millimeter wafers. And we have actually used a continuous argon flow. We use a continuous ICP power, but it's really leads to, without bias, low ion energy. So we're not having any sputtering or anything of the surface. And then we have a very short chlorine dose. We have some special hardware to dose it very precisely. That chlorinates the surface, leads to this modified surface. And then we have a bias step where we again have quite controlled how to do a very precise bias. It would be an RF bias, but we're considering also this other methods of biasing. And that then removes this layer. And we actually have the ICP power on continuously, so the argon plasma continuously there. And we've noticed that it also makes it easier to not having to turn off and on the plasma constantly, but also that the low ion energy argon plasma helps to purge away any excess chlorine that might be in the system and might be on the walls, keep things hot, etc. So that's silicon. Well, there are actually many processes, and this is the Atomic Limits database website, where I'm also partly involved in the blogs and the keeping the database. And here the ALE side is managed by Nick Chittock and Adri Makis. And you see here, like, where is there anisotropic etching, isotropic etching. And you can see there are not that many processes yet that are getting more and more. You see certain elements common in semiconductors getting more and more materials. But you see certain elements not having any ALE process yet. So I think lots of work to do. Example, which I think is nice to explain a little bit how you would develop an ALE process is ALE of silicon oxide. So first of all, what you would typically do is you take the kind of continuous plasma example and see if you can split it up, unravel it. So continuous etching of silicon oxide would be with carbofluoropolymer gases, CF gases, and some bias. But you can split this up where you have the CF polymer step here and the argon step here. Note that this process is also labeled typically as quasi-ALE because this FC polymer is if you do it longer, you will get more polymer. It gets thicker and thicker. So this step is not really self-limiting. So that makes it kind of a quasi-ALE process. Nevertheless, you can get very nice control. And what was done here, and this is done by Stefano Dall'Orto at LBNL, where we have a collaboration also. He split it up, and you see this FC polymer that modifies the surface, and then the argon step that removes that modified layer, and you can repeat that. And he looked in his work also at the effect of the biasing. So, okay, having, you showed this graph before, having different ion energies. And he saw if you only do the argon, so no CF gases, you see that above about 20 volts, you seem to get some sputtering here. This was just in a test cycle. So these two conditions would be good candidates to further explore ALE. So this is the 19 and 9 volts of bias. And then also if for those conditions you turn on the the etch step included in your cycle, then you see you do get etching. So you don't get any etching with just argon, but you do get etching when you introduce the chemical step. And if you don't have any bias, you actually get deposition. You see here negative etching. So many of our etch systems, you can control the temperature quite well, and you can even cool the wafer below ambient. And we see here at 20 degrees, then the 19 volts, which looked like there was no sputtering, looks like if you do it for quite a long time, then there is still some sputtering. So it looks like the 9 volts is better if you want to have a more classical, more pure, like self-limiting ALE process. There's still a little bit of non-ideal continuous etching here. And then they looked at temperature, and they saw that it is maybe also to do with absorption in the chamber and this mixing layer, the thermodynamics there. It looks like if you are at about -10, you get something that's more flat here. But if you're too high or too low, you start maybe mixing the steps, or there's something non-ideal about the process. So it's less ALE-like. So I think that's another nice optimization to be able to have that. So that's, I think, a nice example. And then something completely different. I talked now mostly about processes with ions. So these would be anisotropic, but now it's maybe nice to look also at isotropic ALE processes. And this example, this is still in development, and it has been developed actually on an ALD system because they are often well equipped to handle the kind of the soak steps that we need. And I'll go a little bit into the chemistry of how it works. It's based actually on the thermal ALE process from Steve George and others, where they use TMA and HF. But here for the fluorination, we're using a plasma. So let's say we want to do ALE of aluminum oxide. We have aluminum oxide. We fluorinate it with an SF6 plasma. But the plasma here is not the etchant, it's actually the modifier. So the plasma modifies the top layer and turns it into aluminum fluoride. Aluminum fluoride is not volatile. It's actually a solid which needs a very high point, it's a very high melting point. But then trimethyl aluminum can react with this layer and turning it into volatile species. So aluminum with some CH3 and F groups that can be removed from the surface, and this then actually etches. But you can imagine this chemical reaction needs some temperature. Let's say 200 to 300 to 400 degrees is something that would be nice to react with that layer. And it also needs sufficient time and dose. So what we actually have an inductively coupled plasma source, but we actually also, everything can be well heated, it's well streamlined, can be well purged. And we have a butterfly valve which we can open and close quickly. So we can close this valve to keep things in the chamber. So in the fluorine step, we have everything open, we are pumping well, we can have relatively low pressure, although we're doing this actually at like 100 millitorr to only have effects of the radicals and not of the ions. And then in the TMA step, we close this valve and we pulse with an ALD valve, multiple pulses of TMA. We're keeping the TMA in the chamber, trying to most effectively use that TMA because it can be expensive precursor. We don't want to waste that. That reacts with the surface. And then if we have sufficient TMA, we might have absorbed some TMA on the wall. So then we fully open up this valve and we pump and purge all the openings and inlets to make sure that in the plasma step, there's no TMA around. And if we do that properly, then we can actually see that over, this is a 150 millimeter wafer, with about 100 cycles, we get a quite nice and uniform etching of about 8 nanometers. So this is still work in development, but I think is very promising. And this will be an isotropic process because the fluorine, it looks in the image here directional, but the fluorine radicals basically can diffuse into structures and at least can have multiple collisions. Radicals can recombine after a certain number of collisions, but typically can survive a few collisions. And the TMA is a thermal precursor. You can, yeah, it's a gas. You can that can go also into 3D structures. I mentioned this already. And then with these processes, but actually also with ALE in general, you can actually do smoothing. You can combine it with ALD. I will not go too much into that. And how you can understand that actually is purely from geometric reasons. So if you have a rough surface, if you would progress that surface geometrically, and that's explained also in this paper, you can see that just from this geometric procession, the surface becomes more smooth, especially for high frequency noise, for small scale features. And we also see that if we look at the RMS roughness. So these solid lines are kind of guides to the eye or actually the model, but the points are is real data. So we actually started with a rough surface. We did ALD on that surface to add a layer, and we see that the film gets thicker and the roughness actually goes already down by the ALD. So even doing ALD can smoothen the surface. And then by doing ALE, we remove a layer and actually we reduce the roughness even further. And because we're repeating ALD and ALE, we could actually repeat this multiple times hypothetically. That's not done here, but you could do this back and forth multiple times to try to get as smooth as possible. So I think that's a very nice concept. And I think this will be very nice for things like waveguides and dielectric interfaces to smooth them to get the best device properties. This brings me to my conclusion. So I don't think I will read this out completely, but ALE has very nice properties due to the synergy and the self-limiting behavior, but still a lot of processes are in development. ALE can be done on standard etch tools, but it's typically kind of small and has some limitations. So I would typically recommend that you have some special hardware for this. And a wide range of processes in development with a lot of interesting possibilities. So watch this space. I would say you can contact me in these ways. And with that, I would like to end my presentation and thank you for your attention.